Here we have kinematics, or in particular, motion along a straight line, wherein we look at the concepts of uniform motion, uniformly accelerated motion, and non-uniform acceleration. So first, let's look at the variables that we will be covering or discussing when we talk about motion along a straight line. Now, kinematics is basically the study of the motion of an object, looking at how the object's position and changes in position, how that is related with the speed and the time of travel of the object. So we have the variables for position, variables for speed or velocity, and variables for time. And of course, we have the variable for acceleration. Motion along a straight line, so we'll limit our motion to be along a straight line, either along the x-axis or along the y-axis. So for the x-axis, position is described in terms of the variable x. And when the object moves from position x naught to final position x, there is a change in position delta x, which we refer to as the displacement of the object. Variable for time is t. When we look at how fast the object's position is changing with respect to time, we have the rate of change of position, which we refer to as the velocity of the object. Unit of position and displacement is unit of length. So you have meters, centimeters, millimeters, kilometers, and so on. Unit of velocity is in terms of meters per second, centimeters per second, kilometers per hour, and so on. And calculus tells us that the rate of change of something with respect to time is simply the differentiation of that quantity with respect to time. That is to say, if velocity is rate of change of position, v, our variable for velocity, v is equal to dx over dt, or differentiation of x with respect to time. Now, if the position can change with respect to time, the velocity can also change with respect to time. We have the rate of change of velocity, which we refer to as the acceleration of the object. Variable for acceleration is a. So a is equal to dv over dt, or a differentiation of velocity with respect to time. dv over dt, so that's basically velocity over time, meters per second divided by second. You have the unit for acceleration, meters per second squared. You also have centimeters per second squared. So some notes before we continue. Again, motion in a straight line. For our discussion, we shall be limiting our discussion to use only either the motion along the x-axis or motion along the y-axis. Whether it's motion along the x-axis or motion along the y-axis, there are only two possible directions for our vectors for the motion of the object. For the x-axis, you have the positive direction, which is heading towards positive x direction. And you have the negative direction, which is heading towards negative x. And then for the y-axis, you have positive direction heading towards positive y, and negative direction heading towards negative y. When you see a problem, mention that the object is decelerating. Deceleration means that the object is slowing down. Note that in some books, deceleration is synonymous to negative acceleration, but for our discussion, that is not necessarily the case. As far as our discussion and course is concerned, deceleration simply means that the object is slowing down. And for an object to slow down, that means that the direction of the acceleration is opposite that of the motion of the object. For example, if the object is moving towards positive x and the object is decelerating, the acceleration is heading in the negative x direction. But if the object is heading towards negative x direction and is decelerating, the acceleration is heading towards positive x direction. Again, deceleration means that the object is slowing down, not necessarily the acceleration is negative. Negative acceleration simply means that the acceleration is heading towards the negative direction. Unless otherwise stated, we will consider the initial position to be the zero position or the origin, to keep things simple. The same goes for initial time. So you would often see discussions in our discussion wherein we no longer consider the value of the initial position. That's because it's taken to be zero. The type of motion that an object will experience will depend upon the acceleration of the object. The acceleration of an object may be constant or it may not be constant. If the acceleration experienced by the object is not constant, the object is said to be undergoing non-uniform acceleration, in which case we have to go back to the two basic equations or definitions of our variables. You have acceleration is equal to dv over dt and v is equal to dx over dt. Depending on the problem, depending on the situation, you might have to differentiate or integrate the equation provided by the problem. Now, if the acceleration is constant, the acceleration may be constant at a zero value. A is equal to 0 is equal to constant. The object is undergoing uniform motion. Acceleration is equal to 0. That means the rate of change of the velocity is 0. The velocity is constant. And for constant velocity, dx over dt reduces to simply delta x over delta t. Velocity is equal to constant is equal to the displacement divided by the change in time. If the acceleration, on the other hand, is constant at a non-zero value, a is not equal to 0, our two basic equations, a is equal to dv over dt, v is equal to dx over dt, gives us several equations that we can use to analyze the motion of the object, rather. The object is considered to be undergoing uniform acceleration. For uniform acceleration, you have the following equations that you can use to analyze the situation or problem. Final velocity is equal to initial velocity plus acceleration times time. V is equal to V naught plus AT. The displacement is equal to initial velocity times time plus 1/2 acceleration times the square of time. Delta x, or simply x if we take x initial to be 0, x is equal to v naught t plus 1/2 at squared. Then you have v squared is equal to v naught squared plus 2a delta x. And then you have the equation for average velocity. For uniform acceleration, the average velocity is simply the average of the final velocity and initial velocity. V plus V naught divided by 2. Average velocity is also equal to delta x over delta t. And that's it for now. We'll continue our discussion in the next video wherein we look at some examples for the motion of our object as we have covered uniform motion, non-uniform acceleration, and uniform acceleration.